Let's begin to look at how delta H and delta S interact together to predict spontaneity. They do this using Gibbs' free energy equation. I'm going to start by deriving the Gibbs free energy equation, which comes from the second law of thermodynamics. Here is a math proof for you. According to the second law of thermodynamics, the entropy change of the universe is equal to the entropy change of the system plus the entropy change of the surroundings, and when something spontaneously happens, that sum is greater than zero. Our definitions for delta S cis can be the heat of the system divided by the temperature of the system, and for delta S surroundings can equal the heat of the surroundings divided by the temperature of the surroundings. If we are at constant pressure, then the heat of the system is equal to the enthalpy change of the system, and the heat of the surroundings is equal to the negative enthalpy change of the system. So our substitutions are going to be, for delta S cis, we will use the enthalpy change of the system divided by the temperature of the system. And for the entropy change of the surroundings, we will use the negative enthalpy change of the system divided by the temperature of the surroundings. So this is our substituted equation. Entropy change of the universe is equal to enthalpy change of the system divided by temperature of the system minus enthalpy change of the system divided by temperature of the surroundings. And when something spontaneously happens, the sum of these two will be positive. Let's look at a scenario where water is surrounded by a region at 270 Kelvin. This is below freezing. So our water at 0 degrees Celsius is surrounded by an atmosphere that is below 0 degrees Celsius. So we know from being alive, a spontaneous change will happen. Our liquid water will become solid. Heat is going to flow spontaneously from hot to cold. I trust you realize this is true again from personal experience. So we have a warmer area here and a colder area here. So we know that heat is going to flow out of the liquid water. So our system will lose heat. So this will have a negative value. Our surroundings will be a negative, which gives us a positive because the surroundings will gain heat. You notice the font size is different though. The positive sign is much larger font than the negative sign. This is because the denominator is smaller. Temperature of surroundings is smaller than temperature of system. So if we have the same numerator, the positive sign must have greater magnitude than the negative sign. So this holds true. The entropy change of the universe is greater than zero when this transformation happens. Would you like to see it the other way? How about if we have liquid water at 100 degrees Celsius surrounded by a region that is higher in temperature than 100 degrees Celsius? We know that the water that's in liquid phase will transform to gas phase because heat flows spontaneously from hot to cold. So my higher temperature will start flowing into my lower temperature. So in terms of the system, which is the water, the enthalpy change of the system divided by the temperature of the system will be endothermic. It will be positive because the system gains heat. On the other hand, the surroundings are, of course, losing that heat. This is an endothermic process. Once again, you notice the font of the positive sign is greater than the font of the negative sign. Why would that be? The same reason. The denominators are different. The symbol for the surroundings has a higher temperature than the symbol for the system. So we have a greater positive sign than negative sign value. the sum of these two will result in a positive. So once again, when something spontaneously happens, the universe is getting messier. Now we can take our equation that has been proven and derive the Gibbs free energy equation. We are going to first substitute the entropy change of the surroundings for minus enthalpy of system divided by temperature of system. This will be a true statement at just the end when the spontaneous change is occurring. Now I'm going to multiply this entire inequality by negative temperature of system. I will have a term here that is minus temperature of system times the entropy change of the universe, and this will be equal to the minus temperature of the system times the entropy change of the system, and then a minus times a minus gives us a plus, and this temperature of system goes away. So we have plus the enthalpy change of the system. And remember, when you use a negative multiple on an inequality, you change the inequality direction. So this sum is less than 0. The sum of these two, which is less than 0 when something spontaneously happens, is equal to a term that we give the name delta G. Delta G is minus temperature of system multiplied by the entropy change of the universe. So this term takes into account what's happening in both the system and the surroundings. We give this term a name. Delta G is known as free energy. So when delta G is negative, the system releases energy which we can use to do work. So for all spontaneous processes, enthalpy change minus temperature times entropy change are less than 0. So now you can see how these two variables, enthalpy and entropy, interact. Entropy can be dialed up or dialed down depending on the temperature at which this change is occurring. Spontaneous processes are ones that go to lower free energy, which means that the sum of these two is negative. Enthalpy change can be in joules or kilojoules. The temperature must be in Kelvin, and entropy change is typically in units of joules per Kelvin. So you can see that the units of delta G are energy units, joules. So looking at this equation, what contributes to a negative free energy change? Well, certainly it would help if enthalpy change were negative. If this were a negative value, it would contribute to delta G being negative. So reactions in which we go from high potential energy to low potential energy, so we might be going from, for phase changes, gas to solid, or for chemical reactions, from weak bonds to strong bonds. We also would need a positive entropy change. The entire term here is minus T delta S. Temperature is in Kelvin. That is never a negative value. So in order to keep this entire term negative, entropy change must be positive. This means that reactions which go from concentrated energy, like solid or ordered systems, to dispersed energies, such as gas or disordered systems, are preferred by Mother Nature. So now I hope you see it. In Jurassic Park, when Mother Nature is in charge, what happens? The fences become depowered and lose their energy, and the dinosaurs spread out around the park. Let's look at some different scenarios of signs with delta H and delta S. There are 4 combinations of positive and negative. First, we'll start with delta H negative and delta S positive. That means this entire term is negative. Is there ever a situation in which two negatives can be added to get a positive? No. Delta G will always be negative. So this is an exothermic reaction that spreads energy. This is something that will always be spontaneous, and delta G will be negative. It has two good conditions, exothermic and spreads energy. So when Mother Nature looks at that, she says, go, go, go. Here's an example, putting sodium metal in water to make hydrogen gas and sodium hydroxide. We're going from 0 moles of gas to 2 moles of gas. So entropy change is positive. And if you've ever seen this done, it definitely gives off heat. It is exothermic. So anybody should be able to get this reaction to work. It does not matter what the phase of the moon is. Let's try another set of conditions. Delta H is positive and delta S is negative. That means the entire term minus T delta S is positive. Can you add two positives together and ever get a negative? Well, no. Delta G will always be positive for this set of signs. This is an endothermic reaction that concentrates energy into fewer states. This reaction will never, ever happen spontaneously. Here's an example. If you go to a lake, there will be water and there will be oxygen in the atmosphere. Have you ever seen signs at the lake that say danger, peroxide patch? Well, unless there is a chemical company that's had a recent spill, no, you have never seen this. So this tells you this reaction does not happen spontaneously. We're going from 1 mole of gas to no moles of gas, so we are concentrating energy into fewer states. This reaction also, if you look at bonds broke minus bonds formed, you'll find out that the enthalpy change is positive. This will never work spontaneously. At some point, we'll be discussing how to put energy into a system and make non-spontaneous reactions work, but it's like pushing a broken down car uphill. These two variables are both a stop sign to Mother Nature. Endothermic and concentrates energy. So Mother Nature says, stop, stop, stop. How about this combination? Delta H is negative and delta S is negative. That means the entire term minus T delta S is positive. Can you add a negative and a positive and get a negative? Well, sometimes. It means that the delta H term has to be more important than the minus T delta S term. We can't change delta S, but we can change the temperature. If temperature is small, this term becomes negligible, and delta H is important. This is an exothermic reaction, which is good, but it concentrates energy. An example is a phase change. If we consider liquid water going to solid water, we are going down on both the enthalpy and the entropy diagram. We're concentrating energy in fewer states, and we have to pull heat out of the liquid to make it a solid. So this is an exothermic reaction. So folks, when do things freeze? At high temperature or low temperature? Well, of course, low temperature. So as long as the temperature is low, which means T delta S is smaller in magnitude than delta H, this change will happen spontaneously. So newsflash for you, stuff freezes when it's cold. This is a scenario where we have Mother Nature saying, go and stop. So we need to be in the situation where go is much louder than stop. Here is our last combination. Delta H is positive and delta S is positive, meaning the term minus T delta S is negative. Can you add a positive and a negative and get a negative? Well, yes, as long as this negative value is large in magnitude. We could describe this as an endothermic reaction that spreads energy. Endothermic is a stop for Mother Nature, but spreads energy? That's a go. Here's an example, again a phase change. When water liquid becomes water in the gas state. We go from 0 moles gas to 1 mole gas, so entropy is increasing, but as you notice, it's an endothermic process. We have to put energy into the system to make this transformation occur. So energy being dispersed is good if you consult with Mother Nature, but a reaction that requires heat is not good. It's a stop when you consult Mother Nature. So as long as the temperature is high, meaning the magnitude of T delta S is larger than the magnitude of delta H, this will happen. So once again, a news flash for you. Stuff evaporates when it's hot. Here is our reaction spontaneity summary. At low temp, delta G is the same sign as delta H. So we can consider delta H our low temperature term. At high temp, delta G is the opposite sign of delta S, unless delta S is very close to 0, in which case, refer back to Rule 1. Delta G is the same sign as delta H. So we refer to the second term in the equation, minus T delta S, as our high temperature term. Here is the summary of the different combinations that result in different signs for delta G. Reactions that are negative positive always are spontaneous. Reactions with the exact opposite sign, positive negative, are never spontaneous. I hope it helps to recognize that plus plus goes with high temp and minus minus is spontaneous at low temp. For those of you who like to think of this graphically with the slope of a line, here's another way to think about it. When delta G is negative, we are in the go zone. When delta G is positive, we are in the stop zone, meaning non-spontaneous in the forward direction. A reaction that is negative positive has a starting point that is negative and a slope that is also negative. So it stays in the go zone all the time. A combination that is negative, negative starts at a negative value, but the slope is positive, so it will transfer from the go zone to the stop zone. The go zone is at low temperature. A positive positive starts in the stop zone, but the slope is negative. So eventually, at high enough temperature, we're back to the go zone. And finally, positive negative, we start in the stop zone and the slope is positive. So we stay in the stop zone. We just cannot get to go. So now we're back to our original question. Can we predict if a process will occur on its own? Now we know temperature is involved. So which will be spontaneous in a room at 37 degrees Celsius and minus 10 degrees Celsius? Let's look at 37 degrees Celsius first. We know that evaporation of the water will occur. Why is that? Well, if we look at the phase change for evaporation, it is from liquid to gas. This is what I would call a positive scenario. And positive is spontaneous when the temperature is high. That's because the increased entropy drives the reaction forward. What is spontaneous at minus 10 degrees Celsius? Freezing of the water. Let's look at that phase change. This is a scenario that is negative, negative. So this is something that works at low temperature when the enthalpy term is important. So while energy being concentrated is not wonderful for Mother Nature, the fact that it is exothermic is what drives this forward at low temperature. Many of you like to use actual numeric values in these calculations, and we can a little bit in Chem 101. There's much more calculation in Chem 201, but I'd like to show you an example for a reaction where delta H naught is a negative value and delta S naught is also a negative value. This is the equilibrium between nitrogen dioxide, which is a brown gas, and dinitrogen tetroxide, which is a colorless gas. Before I show you the video, let me show you the calculations. At 15 degrees Celsius, which means 288 Kelvin, our minus T delta S will be minus 288 times our minus 0.177 kilojoules per Kelvin mole. When I take this multiple and add it to the value of delta H naught, I get a negative delta G value. That means the reaction goes spontaneously forward to make colorless product. So in a moment when I show the video, I hope you notice that at low temperature, the mixture is colorless. What happens at high temperature? Now instead of 288, we use 353 for our Kelvin temperature. This makes the magnitude of this minus T delta S term more important than the delta H term, and we get a positive value for delta G naught. This means don't go spontaneously forward. In fact, when we get to equilibrium, you'll realize this actually means go backward, shift to reactant. And sure enough, you may notice that at high temperature in the video, the reaction appears to be brown.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
If you think about this, this is counterintuitive. The reaction prefers to go forward at low temperature. Most people's gut reaction when something isn't working is to crank up the temperature. That does not help in this case. For phase changes, we can always know the signs of delta H and delta S thanks to our handy diagrams. Remember, we have a relative potential energy diagram for enthalpy and a relative disorder diagram for entropy. Going up on these diagrams from, say, liquid to gas results in delta H and delta S being positive. Going down on these diagrams, such as from liquid to solid, results in both delta H and delta S being negative. So here is a question for you. Determine the relative values of delta G, delta H, and delta S when water freezes. The reaction is happening. So that should tell you something about the sign of delta G. When something happens spontaneously, delta G has a particular sign. And then just use your diagrams from before for phase changes. How about a different scenario? This time, acetone is evaporating.